All right. Good afternoon, everyone, and thanks for attending the CAR webinar today. I am Farhad Salimi, and I'm a postdoc at CAR, and will host today's seminar for you. Today's presenter is Professor Zoran Ristovski, who is an atmospheric scientist at QUT with over 20 years of experience in the general area of airborne particle pollution. His main research areas are characterization of vehicle emission-related nanoparticles, their physical and chemical properties, transport in the atmosphere, as well as their toxicity. Just a few things that I would like to mention. Can I ask you all to mute your microphones just to reduce the background noise as much as we can? Thank you. So now I would like to ask Zoran to start his seminar titled Particulate Emission from Biodiesel Fuels, Are We Going Towards Cleaner Biofuel? At the end of the seminar, we'll have 10 minutes for Q&A that you can type your questions, and Zoran and I will read it loud and Zoran will answer. Thank you. Zoran can start.
Thanks for the introduction, Farhad. So, as Farhad mentioned, I've got around 20 years of experience in this area, general area of airborne particle pollution. But what I specialized and where most of my work was done was in the emission or vehicle emission, diesel engines, petrol engines, and looking at the nature sources, transformation of these emissions in the atmosphere, how toxic the fuels are, and similar things. So what I'll run you today is the research that's been going on in my group for the last, I don't know, maybe 10 years, when we started looking at biodiesel fuels. So before I go into more specific research, I'll just give a short intro on the lab where I work with. I'm sure you know some of these people from as CAR's members. So I'm part of the ILAC, International Lab for Air Quality and Health, and that's where I work closely with my colleague Lydia Moravska, but also with my younger colleague Branka Miljevic. Besides that, a really important part of my research is being done to what used to be the ARC Center for Free Radical Chemistry and Biotechnology. It's been finished by now, but then I just wanted to highlight two of my close colleagues who work with there. That's first of all Stephen Bottle, who is responsible for bringing me into the area of free radicals and reactive oxygen species, and also our joint student Svetlana Stevanovic, who is now a lecturer at Deakin University. And also, all this work has been done in the biofuels engine research facility. That's the facilities which I set up together with my colleague Richard Brown around 10 years ago, and it's currently, I think, the best engine research facility when it comes to vehicle emissions and emission measurements in Australia. It's called the Biofuel Engine Research Facilities because we mainly look into biofuels. So where's the interest coming, and why are we so interested in diesel exhaust? As one of the breaking important things happened in 2012 when diesel exhaust was pronounced cancerogen group 1 to humans. And also the gasoline engine exhaust was pronounced cancerogen group 2B, so possibly cancerogenic to humans. This was really a groundbreaking thing because it got a lot of industries to look more seriously into the issue of diesel exhaust. And what was behind this decision was also a really groundbreaking, interesting study published at the same 2012, the diesel exhaust in miners study. And I'm sure most of you know the background of this publication, that it was actually under hold or was under litigation for years between the lobby lobby groups from the mining industry and NIH, who was behind this. So it took them like 10 years, I think, until they got to publish it. But once it was published, it was really an important one, and it led to the decisions in 2012 by the WHO. Also, important point was when in October 2013 that the WHO and IRC has classified outdoor pollution as well as cancerogenic to group 1, with particulate matter, a major point of this air pollution, evaluated separately. So these were all sort of really important major studies and got a lot of the industry, especially the industry which I worked a lot with, which is the mining industry, to think twice on the quality of the fuels they use, the engines they used, and how to improve the emissions from their diesel engines. So then we asked ourselves, why biodiesel? So why do we have to go to biodiesel? Well, we have to be aware that based on current production scenario, we will be running out of oil that we dig from the ground. There's some estimate that the peak production we already reached the last few years, or we will reach by 2030. So we will be producing less and less, be able to produce less and less, or dig less and less oil from the ground. So we have to find some other alternative for a sustainable carbon neutral transport. You know, we're all pushing at the moment electrical vehicles, etc., but it will still take some time before the electrical vehicles will really take replace the normal fleet. So that won't happen that long, and therefore we have to look into the development of sustainable long-term alternatives, and biodiesel could be one of those sort of bridging stones until we come with a totally carbon neutral or carbon free even transports, electrical vehicles, for example. One of the things that's important when we look with these biofuels, and that is that biofuels come from various stocks, so various sources, and that also leads to a significantly different composition of the biofuel, as compared, and biodiesel specifically, as compared to your standard petrol diesel. And then the thing we wanted to look into is how does the composition of biofuel first affect the primary exhaust emissions, so emissions that come directly from the exhaust, and then later on we'll talk about how the biofuels affect the secondary emissions, so the potential of the fuel to produce secondary emissions. And the first study that we started doing in our lab was, slide to change, was we looked into ethanol as a potential fuel in diesel engines. So we'll go into detail how we managed to get ethanol into a diesel engine. But let's say we had a device that enabled us to replace diesel fuel with ethanol up to 40% in energy, which means that 40% of the energy of a running diesel engine actually came from ethanol. So sort of, and then we looked at how does at different loads adding more and more ethanol influence the particle mass emissions. So we see this graph show up soon, yep. And on the x-axis, you have the percentage of ethanol. So E0 indicates pure diesel, E10 means 10% ethanol, and up to E40, which is 40% ethanol. And the bottom part indicates the load of the engine, so idle to 100% full load. So what's clear is that as you add more and more ethanol, your particle emission significantly drops down. Especially evident is this here reduction between the particle emission at pure diesel at 100%, so full load, and then when you replace 40% of the diesel with ethanol, you see a significant decrease in the total PM emission. So the question was, how is that achieved? How can you get, this is almost fivefold decrease in the total particle mass emissions. One way to understand that is to look into the size distributions of particles coming from engine running on pure diesel and engine running on ethanol. So this is the number concentration of particles, and this is their size in the range from 10 to around 500 nanometers. And we can see that with diesel, most of the particles are much larger, at around 100 nanometers. When you add ethanol, these 100 nanometers, that's actually your soot particles, almost disappear, but you get a huge amount of these very small, so nanoparticles in the 10 to 20 nanometer size range. So you do reduce significantly your total particle mass, but your total concentration of particles actually goes up. And what we also saw, and we'll talk about that later, is that the oxidative capacity, or how, let's say, a measure of toxicity of the particles, also shot through the roof with the introduction of ethanol. So if you just follow purely on your regulated emissions, you see that this is really not, the regulated emissions significantly improved, but if you scratch below the surface, you see that there's many problems hidden there in the emissions themselves. So then we continued in this direction and did more work where we now look at the composition, at the particle emission for various different biofuels. So we used 3 different biofuels stocks, biofuels coming from soy, biofuels coming from canola, and tallow or animal fat. And then we mix these biofuels at different blend percentages from 20 to 100% and looked at the particle emissions. And this is sort of what we got. So on the x-axis, you have the blend of the biodiesel. 100 means pure biodiesel, and this is 0 means pure diesel. And on the y-axis is particle mass emissions. And when we see that once we start adding the biofuels, the particle mass emission significantly goes down. And also importantly, we see that there's a strong dependence on the stock. So some stocks, such as soy, have a smaller reduction than canola, etc., etc. So there is some stock dependence, or the compositional dependence of the emissions on the composition of the fuel. So that's the particle mass emission. When it comes to particle numbers, the situation is somehow different. So we see that this is your pure diesel, and we see that even with certain blends, such as tallow or canola, you're getting the smallest particle mass emission, but your number emissions are even larger than biodiesel. So how is that possible? You're getting more particles in numbers, but less in mass. So if we look at the particle size distribution, we can see that the fuels which produce larger particle number emissions, small v here, actually produce smaller particles. So by making particles smaller, you significantly reduce your particle number emission, your mass emission, but your particle mass emission can, number emission, sorry, can go even up. So you're getting less mass, but more in number. Then another important measure, which is very often tied to how toxic the particles are, is the surface area. So the black graph shows the average surface area of particles versus the blend percentage, and we see a reduction in the particle surface area, but the particles are carrying more and more of organic material. So they're becoming smaller, having a less average surface area, but are having more on the condensed organics on the surface of it. And I'll come to the importance of the condensed organics later in the presentation. So we saw that, yes, there are different stocks give a different particle, both mass and number emissions, but we didn't really look in detail into the fuel composition. So then we did another study where we managed to control the composition of biodiesel in a much more controlled manner, and to look at the influence of the molecular structure, the structure of the biodiesel molecule on nanoparticle emissions. So for those of you who are not sort of aware how most of your fatty acid methyl ester biodiesels are made, is you start from a triglyceride, let's say tallow fat, and adding methanol in the presence of a catalyst, you break these chains and you get fatty acid methyl esters. So with the alkyl fragments, they depend on the fatty acid profile. So these are purely hydrocarbons, so long chain hydrocarbons. But what is in the fuel left is, so you've got your long chain hydrocarbon on one side, and you have the methyl ester part, which contains 2 atoms of oxygen. Important to note that your diesel that comes from the ground is a pure hydrocarbon, so it doesn't have any oxygen in it, while the biodiesels all have fatty acid methyl ester biodiesels, or have at least 2 oxygen atoms. So what we did, we managed to get our hands on a stock of biodiesel fuel coming from palm oil, which had controlled carbon chain lengths. So these alkyl fragments were of a controlled length. In your normal biodiesel, they're all mixed up. So for example, they are a mixture of various length, carbon chain length in your normal biodiesel. We got more pure sort of biodiesel, or these fatty acid methyl esters. And this just shows the composition. So for example, our fuel, which we labeled C810, had mainly caprylic and capric acid, which had 8 or 10 carbon atoms in it. And then other fuels we had with a longer chain length, and then some fuels with a large number of different values of saturated and unsaturated bonds in between the carbon atoms. So we wanted to look into how does the carbon chain length in your biodiesel actually influence the emissions. So the question is, can we come up with an optimal composition of the fuel that would give the best performance of the engine, but at the same time give the best emissions? So this is the molecule that we looked at, so the biofuel molecule. And on this here we show for 2 laws. We can just look at one of the graph. So we have the different fuels, 8 to 10 carbon chain length, up to 18, 22 carbon chain length. And this is the brake specific or particle mass emission. So the more biodiesel fuel we add, so this is pure diesel, 20, 50, and 100% biodiesel, we see a significant reduction in the particle mass emission. But what is also interesting is that the shorter the carbon chain length, the smaller the mass emission for all possible blends. And you see this? So when the carbon chain length increases, so does the mass emission. So what happens with the increase of carbon chain length in this oxygen? So this carbon chain length here becomes longer and longer, which means that the percentage of the oxygen in the whole molecule actually goes down. So if the oxygen percentage goes down, the PM goes up. But also we see that if we have more unsaturated carbon bonds, the emissions also go down. So what you would want to have is a fuel with the biggest oxygen content and with the largest number of unsaturated bonds in between the carbons. And that improves your particle mass emission. So when we put that together, for all the fuels we tested, we found an interesting property, and that the specific particle mass emission in our case was proportional to the oxygen content in the fuel. So the more oxygen you had in the fuel, the smaller the mass emission. And we got, actually in this case, an interesting thing, is that the particle number emission also went down. So you were not only getting smaller particles, you were also getting less of them. So that was fairly important thing. We looked at other fuel properties and found that other fuel properties really didn't have a significant influence in the particle mass and number emissions. The trade-off is that your fuel consumption unfortunately goes up with the fuels with a higher oxygen content. So although you're getting better emissions, you are using more fuel. So that's the same slide with the particle mass emission. So the question is, we asked ourselves, why are particles becoming smaller? So what makes particles from biodiesels smaller, the soot particles, than particles coming from your normal fuels? So we did a study where we collected these particles on transmission electron microscope grids and then look at the structure and the size of the particle. This is a typical example of a biodiesel particle. So what you see is that it consists of these smaller primary particles. They are sort of agglomerates in structure. So even this is even nicer. So that's your typical biodiesel diesel particle. You see they are agglomerates of primary particles. So they are around, I don't know, 100-ish nanometers, or these were around 200 nanometers in size, and they consist of these primary particles, which are somewhere of 10 to 20 nanometer in size. So what we found is that the more oxygen content we have in the fuel, the smaller this primary particle will become. So this is your diesel, and this is 50%. This is some diesel made out of hydrogen. I won't go into that. But with 50% biodiesel, the primary particle size was going down. And we repeated this study, and we're currently running a similar study looking into much more detail and a larger oxygen content, and we are clearly seeing that effect. So the way the biodiesel achieves a smaller mass emission is by producing smaller primary particles. We also went into looking at the structures of these particles, so these primary particles in high resolution transmission electron microscope. So what you see here, this is a layer of carbon atoms. There's another layer of carbon atoms. So you see that these primary particles have this core shell structure, and the distance between the layers also depends on the percentage of biodiesel, with biodiesel having a smaller distance between the layers. But what's more important is that we found that biodiesel particles, the bonding in between the carbon atoms, the soot atoms, in the soot emitted from biodiesel is more prone to so-called sp3 hybridization than sp2 hybridization. What does that mean? That means that the atoms in a soot coming from biodiesel are more an amorphous structure than atoms coming from soot from diesel engines, which are more a graphitic sp2 layer structure. But also important is that biodiesel has a much larger percentage of oxygen atoms on its surface of the soot, which means the soot is more oxidized. And this could be one of the reasons that a number of studies have found that the biodiesel, that soot with a larger ratio of the oxygen content on the surface, shows a bigger response. Cells exposed to soot with larger oxygen content on the surface show a bigger response and seems to be more toxic. So we are now repeating this study in much more detail just to confirm if this is valid for various biofuels. This was done only for one type of biofuel. We also looked into characteristics of engines running biodiesel in different in transient emissions. So all the previous studies were done at steady state. So you load the engine at a constant load and you run it, and then you look at the particle emissions. Then we also looked at transient, so how you drive the engine in a normal sort of conditions. On the road, you would go faster, slower. And then we looked at the advantages and disadvantages of having biodiesel. So the main advantage, again, is your PM and PM number, particle mass and number emission goes significantly down. But disadvantages is the known one NOx goes up with biodiesel, and also a significant decrease in engine power, which means there's more fuel consumption in the whole thing. So this was all purely looking at particle physical properties. So let's sort of make a small stop and a digression, and I'll talk now on the relationship between particulate matter and health effects, and how we developed methods to measure or to estimate what is the oxidative capacity of particles. So why is the oxidative capacity of particles important? Because one of the proposed mechanisms of why particles, any particles, are toxic, and specifically combustion generated particles, is that the particles carry on themselves free radicals or radioactive oxygen species. Once they get into contact with human cells, they cause oxidative stress, which leads to inflammation, cell injury, and eventually death itself. So the measure of the reactive oxygen species would or should give a way to estimate what is the toxicity, indirect way of measuring the toxicity of the particles. So I'll skip one slide. So our motivation was, as I said, to develop a cell-free assay, so an assay which we would use without the presence of a cell for routine screening of the oxidative potential of particulate matter. So looking how what oxidative stress would a particle be able to put upon a cell once it enters the cells. And there's also, we are developing monitors of that. So what was our basis of our measurement of the oxidative capacity of cells and our probe? Well, we started with the so-called perfluorescent nitroxide. So perfluorescent nitroxide is a molecule which consists of a fluorophore and a nitroxide part. In its normal state, the fluorophore is not fluorescent. If the nitroxide part, through either reduction or oxidation, reacts with a reactive oxygen species, there's a transfer of an electron transfer between the fluorophore and the nitroxide and the fluorophore becomes fluorescent. So if the perfluorescent nitroxide reacts with a molecule of any kind of ROS, then it will become fluorescent. And that's the process. So simple as that. What we have to do is to find a way how to get the reactive oxygen species on the surface of the particles to react with these nitroxides, and then measure the change in the fluorescence. So to do that, the fluorophore, the fluorescence of the fluorophore is really important. If you want to apply this method to measure the oxidative capacity of combustion generated particles, specifically diesel, you have to have your fluorophore to have an excitation wavelength which is not too low, so you would not initiate the normal fluorescence of diesel or any kind of combustion aerosol. So your natural fluorescence of combustion aerosols will not overlap with your fluorophore fluorescence. And for that reason, we found that the most optimum molecule is this one. I can't even say the full name. It's called DPNH nitroxide with the following structure, and this is an example of the solution which contains this fluorophore, the perfluorescent nitroxide, when it's not exposed to combustion aerosols, and when you blow a bit of cigarette smoke inside, it becomes strongly fluorescent. So we use the measurement. I won't go into details of the actual way we apply this, but we, by measuring the change in the fluorescence of particles solution before and the solution before and after exposure to particles, we estimate the concentration of reactive oxygen species. So going back to that measurement that we did with the biodiesels of different composition, if you remember, what we saw is that the particle mass emission goes significantly down, but what we found is that the concentration of reactive oxygen species per milligram of particulate matter also significantly goes up with more biodiesel in it. And what's interesting, we didn't see any dependence on the feedstock. So the more biodiesel you have less particle mass, but it seems that the oxidative capacity of this biodiesel is larger. What we found, an interesting correlation, is between the organic volume percentage on the surface of the particles and the concentration of reactive oxygen species. Then we went and did a more detailed study of this, where we looked at those biodiesels to which we could control their composition, and also found that there's a direct correlation. Let's just look at one of the graphs between the oxygen content and the percentage of particles that are volatile. So the more oxygen content, the more volatile organic material you will have on the surface of the particle. But interestingly, the reactive oxygen species follow a similar trend. Not exactly, but there is a correlation. There is the more oxygen content, the more reactive oxygen species you have in your biodiesel emissions. So if we try to plot the amount of organic material on the particles versus the reactive oxygen species, the amount of the oxidative potential of particles, we actually didn't get a good correlation. So this is the percentage of organics for various tested, and this is the oxidative potential expressed on concentration of reactive oxygen species, and we see the correlation is a little bit all over the shop. So what we did is we looked at the actual chemical composition of the organic materials that are on the surface of the particles using our aerosol mass spectrometer. And this device we use two specific MZ values, MZ44 and MZ57, when we look at the composition of the organics. This is the MZ mass. MZ44 is a marker of the so-called oxygenated organic aerosols, and MZ57 is a marker of hydrocarbon-like organic aerosols. So what we find is that with more biodiesel, the larger the fraction of oxygenated organics is versus the non-oxygenated, the hydrocarbon-like organics. Then we said, okay, is there a correlation between the amount of oxygenated organics and the reactive oxygen species concentration or the oxidative potential? And when we put the percentage of oxygenated organic aerosols on the x-axis, so what fraction of your organic material on the surface of diesel is oxygenated, we got a nice linear relationship for some of the fuels we tested. So the more oxygenated your organics are, the higher their oxidative potential is. And we repeated that study with various different fuels, and every time we get sort of a nice correlation between the F44 fraction of oxygenated aerosols and your oxidative potential. And we even try that with different types of assays to measure the concentration of reactive oxygen species, such as the DTT assay, and we always find a similar or fairly good correlation independent of the assay we use. And then we also that also confirmed that the oxygen content is fairly proportional to the oxidative potential in the fuels that we have tested, and that the oxygen content is also proportional to F44. So the more oxygen you have in the fuel, the more oxygenated organic aerosols you will have on the surface of your particles. So the picture is developing that although you are getting less of particulate matter for biodiesels, what seems to be is that the amount of reactive oxygen species, so the oxidative potential of these particles, seems to be larger. But an interesting thing also that we looked into is these reactive oxygen species can be found both in the gas and the particle phase. And this is an interesting graph showing the oxygen content in the fuel and the amount of particles, reactive oxygen species that are in the gas phase versus the ones that are in the particle phase. And what we see, the more oxygen in the fuel, the more oxygenated your organic aerosols, your organic material will be, and therefore more of it will stick to the particle phase. So more oxygenated organics have a smaller saturation vapor pressure, and they more easily condense onto the particles, but they also increase the concentration of reactive oxygen species. So most in fuels with high oxygen content, most of your reactive oxygen species is in the particle phase, while less in the gas phase. But this also raised the issue, the importance of the concentration of reactive oxygen species coming from diesel or any kind of combustion emissions in the gas phase. It is still significant. So to summarize, the ROS concentration, although proportional to the total organic volume percentage, shows much higher correlation with oxygenated organic fraction. And to confirm this, we continued and did, I'll have to be quick going through these few remaining slides. We did some exposures of human lung cells as well. So I wanted to look how do human lung cells react to organic from diesel particulate matter. For that, we use a Caltex system where we are able to directly expose the human lung cells to diesel exhaust. So we don't capture diesel exhaust into liquid and then mix that liquid with the lung cells culture, but we directly expose the human lung cells to a flow of diesel exhaust. So what we did is we started with our diesel exhaust with the organic on the surface of diesel exhaust. And then we have a way to remove these organics using certain methods and expose the cells only to particles without these organics. What's important is that only 10 to 20% of the mass has been removed by the evaporation or the removal of organic material. And this is the response of the cells that we got. So you have the cell viability on the y-axis. This is the baseline. This is filtered air. So diesel exhaust passed through a filter where all the particles have been removed. This is normal diesel exhaust. Let's say diesel exhaust with the organic material. And this is diesel exhaust with the organics removed. So we see that the viability of the cell for short-term 30-minute exposures was much larger when we removed the organics. When we went to longer exposures, the situation actually changed. We are not sure what was the reason for this significant difference. Another important thing, and tying this organics to the oxidative capacity, is when we looked at the concentration of the IL-6, which is a marker of how much the cells were stressed on to as a function of different exposures, we see that when we expose to neat diesel, so that means diesel with the organics on the surface, the concentration of IL-6 is significantly larger than with the organics extracted. So we can tie here the organics on the surface to the stress or the reactive oxygen species that they carries into it. So further studies that we are going to conduct and what we want to look into when we're talking about diesel and biodiesel emission, and that is what happens. You want to understand what happens with the exhaust after it's emitted. When we combust diesel or biodiesel in general, what we get is we get the soot. That's the black carbon, if you remember those pictures from the electron microscope. But on the surface, with just green color, although it's not green, we noted the organics which condense, but we also get some tiny nucleation particles inside. So, but also what comes from the exhaust is the volatile organic compounds which are in the gas phase. When the exhaust is emitted into the atmosphere, these volatile organic compounds react with sunlight and OH radicals and ozone, and some of them get oxidized and start condensing onto the surface of the soot particles, adding additional organic mass. But also what happens is that the organics that are on the surface of the soot particles also react with the natural oxidants in the atmosphere and also change the composition or become more oxygenated. What we want to look into, and what the problem is, that the exception of the population that lives close to busy road, the majority of us, human population, is exposed not to fresh exhaust, the ones that we measure directly in our lab from emissions, but to aged exhaust. So exhaust which has spent significant amount of time in the atmosphere. Now and that's the studies that we are currently conducting. We are looking at the changes in the particulate matter when we age it in the atmosphere. So I won't go, I'll have to shorten this presentation. And one of the questions that we want to ask ourselves is, what if we follow with the biofuel mandate? So we increase and we mandate that 10% of all the fuels sell have to be biofuels, and even increase it to 20%. What we know is there will be a significant reduction in primary particle emission. There is no doubt. Will they be less or more toxic? Well, it can go both ways. But what we don't know is what will happen to the secondary particle emission. So if we cut primaries, will we actually increase the secondary particle emissions? And these are the studies that we are conducting now. We are looking at the secondary aerosol production from various biodiesel. So we want to know if we increase the consumption of biodiesel in an urban environment, will that actually lead, or will these future policies lead to a total increase in the particle loading in an urban atmosphere due to the secondary emissions or not? And we do that using our smog chamber, and this is the smog chamber and the experiments that are currently, as we speak, being done in our engine lab. So it's a Teflon bag of 8,000 liters, which we fill with diesel exhaust. Then we turn the UV lights on. It's inside this trailer. And then we grab a sample outside, and with a number of various mass spectrometers and different gizmos and gadgets, we measure the composition of the diesel particle matter after it's been exposed to simulated aging conditions. So overall, to conclude, we need to develop a clear understanding of the mechanisms that drive this secondary organic aerosol formation in order to develop new technologies in urban transport or transport solutions. So the question at the end we ask ourselves, will the biofuels be really that promising clean technology or not? So before I finish, I like to use this example and show this guy. His name is Thomas J. Midgley. Maybe some of you have heard about him, but he was considered as one of the most creative chemists who ever lived. What this creative chemist did is he eliminated the problem of engine knock by identifying the gasoline additive tetryl lead. So this person actually discovered dichlorodifluoromethane as well, or also known as Freon. So they consider Thomas J. Midgley as the most toxic single organism that had ever lived on the surface of the Earth, and who had the most negative impact on the atmosphere than any other single organism. What Thomas J. Midgley did is he looked at two engineering problems and solved them, but not looking at the environmental effects of his engineering problems. And that's what we always have to take into account in developing new fuels or new technologies for vehicle emissions. Thank you. And I'll finish with my group. This is an older picture. The group has now significantly changed.
Thank you.
Thank you.
Thanks, Zoran. It was a very interesting presentation, and I'm sure it's really hard to put all your work in an hour-long presentation. So, but you did a great job, yeah, because you've done so much. So it would have been a challenge for you. Thanks again for coming and giving this presentation. So it's now time that we take a few questions. We have around 10 minutes, and I can I ask you all to type your questions on the chat box? That Anna has already done that, and Zoran, can you read it loud and answer the question? Yes. Thank you. Can you see Zoran? Or you want me to read it for you?
Yes, I can. Yes, I can. So,
okay.
Yeah.
Zoran, Anna is asking, are you looking to do any animal model studies as well as part of your research?
I didn't. No, not the animal model studies. Just doing the cell exposure is more than enough complicated for my taste.
Okay, so while we are waiting for others,
but I know that Ben Mullins in Perth has been doing or is planning to do some mice exposure studies on biodiesel. Biodiesel, we're doing now a literature review on biodiesels and how the toxicity of biodiesels and cell exposure studies, and we are finding contradictory results. Some studies show improvement, some studies show, on the contrary, more toxicity. So it's still open question.
Yep.
Here's a question.
Yes.
You want to read the questions?
Yes, I will do that. And Anne is actually asking whether it's possible that you provide the presentation. I think she wants to use it for her environmental toxicology students.
Yes.
So fantastic. And the presentation itself will be available online. It's being recorded, so it's going to go on the CAR website. And Michael Abramson from Monash is asking, firstly thanking you for the presentation, and he's saying that I have not, it's moving, it's hard to, I have not thought so much about organic chemistry for 45 years. Reduced particle mass and numbers sounds like a good thing, but I'm concerned by the increased reactive oxygen species in biodiesel exhaust. Might these have unexpected toxicity in human populations?
Yes, that is true. And for example, we have advised the mining industry to be cautious with introducing biodiesel into underground mines, because that's a fairly specific environment where you get very high concentrations and with a small ventilation rate. In above ground situation, I think it's still open question, because you do get much less of the PM emission. It is more toxic per milligram, but you get less of it. So overall, you get a reduction. Yeah.
Yep, and Kristen Cowie from University of Sydney is asking, are you planning to look at biofuels as well as biodiesels?
No, currently we are concentrated on biodiesels as per se, and the only reason is all of my engines in my biofuel engine research facility are diesel engines. We are planning to also install eventually a what we call a spark ignition engine. That's your standard engine that you use in most of the cars. And then we will be looking at other biofuels. Ethanol is one thing we also want to look into.
Great. Zoran, I have a question myself. So what do you think about the regulations? We are doing all these studies. Do you think that we now have enough evidence to introduce new regulations, not just to be focused on PM 2.5 and PM 10?
It's not just do we have enough studies? I think we do. But if you ask me, do we have, if we want to introduce some other measures, other metrics such as particle number or something like that, I don't think that we still have as reliable methods and robust methods of particle number measurements or other metrics for particles measurements that we have for mass. So while we can introduce a new standard, the question is how will we implement and monitor these other different metrics. I think that's somewhere where we have to do more research and do more work on.
Christine has another question. She asks, do we have enough evidence for a health impact assessment?
I think we do. I think we do. But as I mentioned, the question is which metric is the most important.
Yeah, and when you were giving your presentation, I was thinking of how important it is not just to think of the engineering side of things to fix technicality issues, but by introducing environmental problems. Like now there is in hydrogen engines now, they are thinking of introducing ammonia to solve some engineering issues that potentially it can lead to secondary particulate matters, which is interesting as well.
Yeah. We're just doing a study again for the mining industry on interaction between ammonia and diesel emissions because of the introduction of those SCR, selective catalyst reduction of NOx, and that adds more ammonia into the air. So will that lead to the changes in the particles and secondaries, etc., etc.? Yes, I agree. There's a question from Christine. What would I suggest is the most important metric? Phew, that's tough. Now, if we look at an ideal world, let's say we have any kind of measurement method, I think measuring these reactive oxygen species is a nice surrogate of particle toxicity, of how toxic the particles are. So while we are years and years away from that being a reliable measurement method that would step outside the lab, if possible, that would be a good, nice, overall sort of integral measure of how toxic the particles are. Still keeping your mass as a measure. I am not sure about the numbers, to be honest. I'm not that much a number person. Was somebody?
Yeah, it said Anne is giving a comment. It would be good to continue discussions about this to how to incorporate these measures into epidemiological studies.
In order to do that, we are working on developing a real-time reactive oxygen species monitor, and we will be doing some evaluation of that here and in China by the end of the year. And you need to have these sort of long-term measurements of all these parameters or properties before you go into any kind of epidemiological studies. And I think we are still away from that. But that's something that we want to move into. But yeah.
Yeah. And just general maybe question. It can be good to conclude as well. How do you see the future of biodiesel? And do you think it has any chance of being widely operational in cars, given your presentation and evidence provided, as well as the recent advances in electric cars? So how do you see that?
I'm not against biodiesel. What I wanted to point out to is that we have to be cautious in what type of biodiesel we are producing. And all of our research was trying to find, is there an ideal formula for biodiesel? So is there a composition that would be the best? And then let's say we genetically modify an algae to produce a fatty acid methyl ester that would give that composition and then produce biodiesel from algae. That's the sort of direction in which we were going. So is there a future to biodiesel? I absolutely think yes, there is. But do we have to look into other technological methods or approaches to improve this sort of toxic properties of biodiesel? Yes, we have to. And now we are looking at different after-treatment devices. One of my students is doing that research and how those different after-treatment devices work with different biodiesels. And does the application of certain after-treatment devices actually improve the situation with biodiesel? And if yes, then we've got sort of a formula in the direction in which should be going. The bigger problem is the feedstock. Can we have a reliable feedstock for biodiesel? And that's what the biggest complaint is, that we can't, so far we don't have a reliable supply of biodiesel that we could really implement a mandate of 10% biodiesel. So have a certain stock that can supply enough biodiesel for the market. So you get a little bit of this, a little bit of that, and all those mixtures, and then your engines don't like it, and the after-treatment devices don't like all those changes. So that's a problem. So currently, we still have to improve a lot of our understanding and work on biodiesel before we can implement it.
Thank you. Fantastic. We still have time for maybe a couple of more questions if anyone wants to ask any question. If not, I think it's now time to end today's webinar. Thanks again, Zoran, for an interesting presentation, and thanks to all who attended. And I would like to add that today's webinar has been recorded and will be available on CAR's website. And have a good day, everyone. Thank you.
Thank you. Thank you, Massimo. Thank you for giving me this opportunity.
Thanks, Zoran.
Yeah, goodbye.